Hello class, today I'm going to show you how we can start using Fluent and how we can deal with the simple case of flow analysis. Let's start with workbench. Okay, now we have our workbench. For fluid analysis, as you can see here, we have three main solvers: CFX, Fluent, and Polyflow. CFX is the software ANSYS company developed for the fluid analysis, and usually it's very big for 2D mesh. It needs dedicated post-processor to have the data. For example, mesh adaptation is very weak for CFX, and when we have like every year ANSYS updates the whole software, usually we rarely can see update for CFX. And yeah, so basically ANSYS developed software for fluid, but later they found that they're not good at that section. So what they did, they bought Fluent from other company and they added to our software, to their software package. And Fluent is much better. Fluent comes with the GPU acceleration, very good for 2D, 3D, and yeah, overall we have Fluent is much better software than CFX, and every year they update something, they improve it, engineers improve it. We have a lot of tutorials for the Fluent, and basically Fluent is a software everybody is using, and CFX gradually they decide to get rid of it. What is Polyflow? Polyflow software is like a spatial case software, usually for non-Newtonian fluids. You also can use Fluent, but Polyflow is much better, or for viscoelastic flows. Okay, let's start with Fluent. Before opening anything here, I'm going to tell you a little bit story about what type of equations we are going to solve. When we solve fluid, when we investigate fluid, we usually use term CFD, which is computational fluid dynamics. And when we using this term, we usually mean we are solving at least 4 different equations to get the data we need, or for analyze as fluid, which could be fluid movement or temperature or the species of that fluid. So as you can see here, we have one equation for conservation of mass, another equation for conservation of momentum, conservation of energy, conservation of species, effect of body forces. So these are going to be a set of equations. So you are familiar with conservation of mass. Whatever goes in should go out, otherwise something is created or disappeared, which is not possible. So when we do the numerical calculation and computational computation, we need to keep this balance, otherwise our calculation would be wrong. Conservation of momentum, it's about velocity, which I'm going to show you, tell you more details about that. And conservation of energy is again the balance of the energy. Species would be the type of material we have because of the changing, for example, reactions, mainly for chemical engineers, or sometimes civil engineers use this type of equations. And effect of body forces. Okay, Let's see what type of equation we are talking about. This is the main equation we have. And as you can see, the first term, which comes with time, we call it unsteady term. This phi could be anything. It could be a temperature, then we call it conservation of energy. It could be a velocity, then we call it conservation of momentum. It could be concentration, conservation of species. Okay, so when we have a term with a time variable, we call it unsteady term. When that term multiplied by velocity, this v, it is going to be a convection term. When we have a Laplace equation here, we call it diffusion, and you know what is diffusion. Diffusion means movement in molecular level. Convection is movement in larger level, like when you have a hot fluid, it is going to move from one side to another side. It will be bulk movement. And then finally, the generation term, it could be like you have a heater, you have a pump, turbine, something creating some energy or movement. So the generation term would be that. All this equation is going to generate some partial differential equation, and we are going to convert those partial equations to some algebraic equations, which would be easier for us to solve. Then those algebraic equations will be in a matrix form, and then software basically solves those matrices. And as you can see, Fluent is using this contour volume to investigate. You learned about finite difference. Finite volume is very similar to that, and sometimes even we use some concepts of contour volume to describe finite difference. Anyways, basically ANSYS generates some mesh, some contour volume to calculate whatever goes in and outside of this contour volume, and it should be balanced, or there should be conservation of mass between left and right side, top and bottom. And then ANSYS depends on the problem we have. It's going to solve conservation of momentum, energy inside each of those contour volume, and then expand those for all these points inside, for example, this tube, and we can post-process those data and see, for example, what is the pressure, velocity, or other things. It's better to know Fluent contour volumes are cell-centered. So all the data is going to be inside each cell center. And for CFX, all the data are going to be at node centers. And you know what is the difference between cell and node. And it's not a big deal, but because of this decision, the formula generated would be a bit different. Let's see what are the steps we need to do to be able to solve and use Fluent. You need to define and identify your problem, what you want to do, what you want to identify, and then identify your domain. It is very important to simplify the domain you want to have. And then you need to draw your geometry, make decision about mesh, and then find out what type of physics you have, and then select the solver. Remember, during the lecture I said, don't start simulating a problem if you don't know the physics of that problem. And the main reason was because you need to know what is happening inside that problem. Is it laminar flow or turbulent flow? Totally different story. Is it about like a specific region? Do you have an area which you should focus more, or some other important aspects of that physics? So it is very important to know that. And then after selecting solver, you can solve and then post-process the data. Okay, So we need to know what type of data we need to generate, because usually ANSYS, we can ask Fluent to specify and save those data for us. Especially if you have unsteady term and you are going to have transient simulation, you need to already tell Fluent, I want, for example, pressure, velocity, temperature, every second saved to this folder, and it is going to be time consuming and a little bit, you need to have some enough capacity. So you need to make decision what type of data you want. Also, you need to consider what type of simplifying assumptions you can have and you have to have. We already know about the static structural part. If it was possible to have a symmetry and it was symmetrical, you must use it, because we always have a mesh problem. The computers would be problem. We don't have that much cores to assign for those solutions. So if it's symmetrical, we definitely go and select the symmetry, get the rid of half of the geometry, and then solve for that half. And what type of accuracy you need? It is a really important question, because for some, for example, industries say, no, this accuracy for me is enough. For example, 10 power minus 3 accuracy would be enough. For some other applications, you say, no, 10 power minus 12, which is very high, and you are looking for that accuracy. So you need to know what type of accuracy you need for your data to be able to accept as a result. And again, if it's possible to go for 2D, definitely select 2D. And this figure shows how we can simplify. For example, this is original cat bar, some pipes connected to each other, but we want to simulate fluid inside. So the fluid inside, that T-shape connections would be something like this, which would be much easier for us to simulate, and we can get rid of the solid parts and just have a domain of a fluid instead of having solid and fluid, which creates a lot of trouble about connection between solid and fluid, more details about the sharp points there, which is difficult for us to simulate. So you need to simplify that. And these are the main types of mesh we have: triangle, quadrilateral. And so this blue part is going to show us the type. Tri means this shape, tetrahedron is going to be like this shape, hexahedron like a cube, and the other. So you need to know these first three letters of each to know what kind of mesh you are selecting. For some cases, for example, if you have a flow aligned geometry like this, so flow comes from the, for example, left side and goes to this side and moves from this changing cross-sectional area, you may need quadra-hex mesh. It would be much more accurate, easier to calculate, and accuracy would be higher. For other case, like a very complex geometries like a car or very complex other type of geometries, you may go for tri-tet mesh, which is going to have a prism mesh close to the edge and boundaries to have more mesh close to that area, and tetra for the further from the area of interest or boundaries. The accuracy would be a little bit lower but faster, because the geometry is very complicated and you want to solve as fast as possible, so you go for tet. So I know I'm talking very fast for this part. These selecting mesh is kind of a skill you gradually going to learn, and so you need a little bit time and doing some project, gradually understand, okay, this mesh is better for these cases and the other mesh for other cases. Okay. Yeah. I said it is very important to know the physics, because if it's turbulence flow, you need to have other you need to have some selections for that. Combustion, multi-phases, you have some items and options to select if the physics is different. And the initial values are very important, depends on the physics and the type of problem. If you have inlet and outlet, because inlet is going to have, for example, velocity come in or higher temperature come inside your geometry, it's always better to initialize your values from inlet to have a better energy balance or mass balance. And usually we prefer to go for higher accuracy. Again, it depends on how much time you want to spend for your solution. And let's see what else. ANSYS is going to solve the algebraic equations you generated based on the conservation mass, momentum, energy, and iteratively it is going to solve it till reaching accurate results. But this accuracy is going to be found based on convergence criteria. Sometimes you say, for example, I want this convergence criteria 10 power 3. Usually I think Fluent, the default convergence criteria is 10 power minus 3, which means ANSYS, after many iteration, if the next value is, the difference between next value and the current value is less than 10 power minus 3, ANSYS is going to stop and say, I converged. You can increase that level to, for number 10 power minus 4, 5, 6 till minus 12. Yeah, so this is type of this accuracy for convergence. You need to make a decision. Depends on the physics, mesh resolution, and numerical errors you have. We talked about the flow physics. It's really important to know what type of boundary condition has, exactly similar to static structural. Correct boundary condition is going to affect your results. If you select incorrect boundaries, everything is going to be so much different, and so it is very important to make sure the boundary conditions you are selecting are accurate, acceptable, and you always need to make sure you have adequate mesh, and you can do mesh dependency test or other techniques to check mesh errors you have. And usually we do some rough simulation to know the concentration of the data or the area of importance, and you increase the quality of mesh at that area to have accurate results. Okay, let's go and start our first Fluent simulation. I'm opening geometry or space claim, as you can see here. So for Fluent and static structure, ANSYS use both of them using space claim. Let's decide. For this simulation, I'm going to see what is the effect of a pipe inside the flow stream. Inside the a channel with circular cross section. Let's go with that. So let's select the surface. I can draw a circle here, but I already know I can simulate a half of it. So I'm selecting that half. Why bother simulating the whole object? So 50 millimeter diameter, and I select a half of it. So let's pull it. It it is going to be 80. Okay, now let's draw here. I want to have a pipe. $15, $10, and let's pull this one and cut it. Okay. Let's pull. I'm going to draw 15 again. This time, pull it. Let me undo. I made a mistake there. So I want to draw here. Let's get rid of this. Okay. Now I'm going to select okay, I turned on 3D. Now I want to draw a circle here. Basically, I decrease the size of this pipe. Okay. Done with this. Now I have a pipe inside this flow stream. Let's zoom it. Yeah. As you can see, this is just fluid domain. And this is the half of the pipe I have here. I want to have a flow stream from the left and outlet here on the right, and see what type of flow behavior I'm going to see there. Okay. Let me delete this one. I don't want that. Okay, let's go to the mesh. Now I'm thinking I could go for the even make that one half and have a much less geometry for mesh. But yeah, but you understand what I mean. You need to think about to get the smallest portion possible for your simulation. So I could cut this half and then use it for my simulations. Okay, it's enough, and let's see. I'm going to check the default mesh. Okay, so it's a not very good mesh, I'm going to insert the method. As you know, geometry is selected. Let's apply geometry, and for the method I'm going to go with hex dominant, because we talked about hex dominant must be much more accurate than tet one or the triangular one. And it's I know that the direction of the flow would be from the left to the right, so we already also talked about if you could have like a simple uniform mesh, would be much better for us, and the quality of the result would be much higher. So I'm going to increase the overall quality of the mesh. So this is 4 times 10 power minus 3. I'm going to go with 1. Let's see how much it is going to improve it. If I select that tet one, it is going to be much more faster, but hex dominant takes a bit longer time to generate mesh, and the number of nodes will be a bit higher, so everything would be more time consuming. Okay, let's stop it. It's too much. Let's go for make it twice larger. Okay, let's see. Much better, very uniform, and definitely the quality is going to be better, but I need to have a finer mesh close to the boundaries. So let's go for inflation. This is my geometry. Let's apply. Now it is going to ask me select the boundaries. Boundaries are going to be close to this pipe. So this part, click control, this one, and this one. So all the boundaries are selected. Now I'm going to apply. Let's go for 10, and let's see what type of improvement I'm going to see. Okay, let's see the mesh. Wow, I applied inflation over the boundary area, but nothing changed. If you go back and check the icons close to each of these options I add to my mesh, you can see there is a cross here for inflation. For the other two is green check. So it shows one of these options nullifies my selection here. So I know already that hex dominant is going to nullify this inflation close to this boundary. So I'm going to suppress that and now generate mesh again. Let's see. Now we can see, yes, we have more better quality mesh there. So to improve the quality a little bit more, I'm going to 1.5, and let's see what type of mesh is going to be generated. Okay, even I can go A little bit finer. Let's go with 1. Last time I didn't wait enough. Okay, let's see. Okay, the mesh quality is good. We have higher mesh finer mesh close to. Okay, our mesh is ready. Now we need to name inlet, outlet, and symmetry surfaces. Remember, Fluent knows the naming and checks the names. If I select, for example, inlet, for example, wall number 1, it's not going to recognize anything. But if you select this section as an inlet, which I'm going to do the same, create name selection, inlet, and ANSYS Fluent is going to automatically understand, okay, this is my inlet, the boundary condition of inlet is going to be applied, which is much faster than manually doing everything. This part is going to be outlet. Usually outlet would be outlet pressure, which is the pressure outside of this outlet should be equal to inside, so no pressure gradient there. What else? I'm going to select this one. Wall bend. Let's use wall bend. So it is going to be just wall. What else? Nothing else. For these parts, let's select these parts. These are going to be just walls and no slip condition and stationary walls. So right click, name selection, walls, done. So if you check the name selections, it is going to be inlet here, outlet here, wall, the outside wall, inside wall for the pipe we have there, and one more, I need to select this one as a symmetry surface. So ANSYS is going to copy everything here from the right side to the left side as a symmetry line. So symmetry, done. So this is going to be symmetry. Okay, let's close this and go back, update our mesh, and I'm going to start setup. Okay. Here it shows what type of accuracy I'm looking for. Usually double precision is the good accuracy. It automatically selected 3D based on the geometry I draw. The processing option could be a serial, which is going to use one CPU core, or parallel. I'm going to use, for example, 4 CPU cores. Nowadays our computers come with 5, 7, even nowadays we have 9 cores. So let's use more cores for our simulations. Okay, now it is opening. The first thing you can see is it's a little bit different from the page we had for static structural. Okay, as you can see, we have a little bit difference between the structure of this page with the static structural setup page, because this Fluent software comes with another company, so they have another arrangement. Let's see what we have here. On the left side, we have a tree with different sections. The main title is Setup, Solution, and Results. For each part, we are going to have some subtitles here, which you need to specify to be able to solve a Fluent simulation. Let's see if this is the one we wanted. Yes, this is our simulation case. Okay, for the setup, let's start with setup. The first subtitle is general. You need to select what type of solver you want. Pressure-based, density-based. Usually we select pressure-based. Not a big deal. For velocity formulation, absolute value, relative. Let's go with absolute values. Now here you need to say if you are looking for steady state or transient one. For me, I'm looking for, let's go with steady state. Do you want to have a gravity option or not? I want to have a gravity. And it is going to be negative 9.81 at y direction. So it is correct at y direction. Done. So I selected, it is a steady state calculation, and gravity is important. Model. We have a lot of case. You can select multi-phase. You can turn on the energy, radiation for specific applications here. I'm going to go and select one of these models inside viscous models. It could be inviscid model, laminar, or a lot of turbulent models. Usually I'm going for the simple case, which is the laminar, but these turbulent models are available. I personally developed a code for K epsilon turbulent model. K omega is also very popular models for the simulations. For the larger simulation, for example, civil engineer large eddy simulation, ADS, people use it. And so for different application, you need to do a little bit research to know which type of model people usually use. Let's go with laminar for this one. We're done with the model. Let's select the material. Currently, as a default, for fluid it's air, for solid it's aluminum. I don't have any solid, so I don't want to any change for the solid part, but for the fluid I'm going to create or select another one. It is fluid, and let's select from database, and I want water. You press copy and select. So as you can see, now I have water beside air. Because I have two materials here, I need to make sure for this domain, for fluid domain area, the water is selected as a liquid, not the air one. Okay, we finished with the material. Let's go for the cell zone. Let me click the cell zone to see. Okay, this is the option I have. I have just one domain, and it is fluid. I'm happy, but I'm not sure which fluid is selected. So I go for edit. Oh, it is air, but I want to be water, liquid. So I made sure this domain, the whole area is water. Done with the cell zone. Now I'm going to select boundary conditions. Let's double click it. As you can see, the name selections we had inside the mesh generation page, now they are really helpful. For inlet, automatically velocity inlet for the boundary type is selected, which we like. For outlet, pressure outlet, excellent. For symmetry, automatically ANSYS understands, okay, it is symmetry surface, I'm going to apply symmetry boundary. For this one, wall, for the other one, wall, we are happy. Let's open the wall one. It should be stationary wall, no slip condition, happy. But for inlet, I need to add some inlet velocity magnitude. So I don't know, maybe 20 meter per second would be good. Let's finish that one. So I finished the boundary conditions, and let's go for reference value. As we already talked, ANSYS Fluent needs initial numbers to start our calculation, and if you select the good numbers, it is going to be much more faster, the convergence would be better. So I'm asking the reference or initial the reference values to be selected from inlet. So you can see the initial velocity is going to be 20 from inlet, and when I initialize this solution, it is going to say, okay, let's initialize from inlet, which we have something coming in, and the mass balance and energy balance will be much better. Okay, let's go for solution. What type of methods we have? As you can see, we can select simple, simple C, piezo, coupled. There are different algorithms we can select to solve our algebraic equations. Okay. For pressure second order, momentum second order, least square cell based, we are happy, good enough accuracy, so I'm not going to touch this part. For monitor, as we talked, remember residuals, I said the accuracy of the ANSYS calculation, we can control it. As a default, it's 10 power minus 3. Let's go for 10 power minus 4. So the accuracy would be much better. And okay, so I'm going to monitor this residual when we are solving this problem. Now we need to initialize and make sure we have some initial data inside. And I already selected reference values as an inlet, so it would be much better. I can select a hybrid initialization and click this initialize, or I can select the standard initialization, select the inlet or outlet, depends on the geometry we have. Let's go with hybrid and wait for the Fluent to initialize, and basically it gives some data inside those algebraic equations and solves once. And let's go for run calculation. The number of iteration I'm looking for is 1000, and interval is going to be 1. Hopefully it's not going to diverge, and let's start calculation. Now you can see the residual I selected was 10 power minus 4 for x velocity, y velocity, and z velocity. All they go very close to the 10 power minus 4. For the continuity, it's a bit high, but it is going to gradually get better. Okay, I'm going to pause it and wait to finish the calculation. Okay, I stopped the calculation. We don't want that much to have data, so let's go and see the results. Opening the results, as you can see, I paused it. Okay. So let's start with contour. So I'm going to select this contour. I'm happy with the name, and for the location I'm going to select this symmetry surface, and I would like to see what is the velocity, and the number of contour lines is going to be about 50, for example. Let's apply it. Okay, Now we can see we have velocity about 20 here comes in, and we have lower velocity close to this upper and lower sides of this pipe walls, and high velocity inside, kind of the venturi phenomena happens, and also we have lower velocity after this. As you can see, we have some sharp movements here of this contours, which is because of the large mesh size. I needed to improve the mesh quality, but yeah, just for presentation case, it's good enough. Let's see, instead of velocity, let's see the pressure. As we expected, we must have very high pressure at this 2 point, at the center of the top and bottom walls of this pipe, which they are stagnation points. And you know, stagnation point is the point your velocity is going to be 0, and you are going to have the highest pressure. And interestingly, we have lowest pressure above this one. Okay, now I want to have some, for example, streamlines. Let's see. Streamlines should start from inlet. Yeah, 25 maybe it's good, and it's going to be show velocity. So you can see that velocity streamlines, and they are bended at the top and bottom of the pipe, and we have some straight velocity at the center, and afterward we have something like a vortex happening. As you can see, the streamline is bended. If you want, you can increase the number of streamlines, for example, to 50. Let's see. So you can see the velocity. The red area has a higher velocity, and yellow area lower velocity. So close to this pipe we have higher velocity inside and outside. Okay, let's get rid of this streamline. And vector, I want to see what is the over symmetry over this line, what is the what type of flow pattern we have there. Let's see. As we expected, we have some circulations, high velocity at the center, and at the top and bottom we kind of have a circulation here and here. Even inside, close to the wall, we have circulation. As you know, because we selected no-slip condition, we expect to have some circulations here. So these vectors visually can show us a lot of information about the flow pattern. These vectors are red and close to each other, so higher velocity here, here, here. At the top we have much more higher velocity than the bottom, and here we have some fluctuations and low velocity area. Yeah, let's turn off that one. I want to create a plan over XY plan, so here, and let's go with, for example, I don't know, where is it? Let's see. Apply. Okay, this is the plan I selected, and we called it plan 1. Now I'm going to select contour, turn it on. It was already over symmetry plan, but this time instead of symmetry plan, I'm going to select plan 1 I just created and apply. So now I have velocity or pressure profile over that plan, which is much interesting. And you can see low pressure here. Interesting. It's not total symmetric because I didn't draw symmetrical. Let's see the velocity profile. Wow, very interesting. So low velocity close to the pipe inside here and a little bit here, high velocity at the top and center. Okay, if you had time, play with the others, see the options. Okay, thank you very much. See you next time.